Hey y'all. Today we're going to take a look at graphs of polynomial functions, and then we're also going to get into end behavior. A lot of stuff that we're doing today is very conceptual, but it's still going to help us make connections and be able to graph our own polynomial functions that is coming in a couple of days. So I'm going to start with just the general shape of a few functions. Now, we tapped on a few of these general shapes a few weeks ago, but I'm bringing it back up today since we're in the polynomial unit. So I'm going to go through a constant, a linear, a quadratic, a cubic, a quartic, and a quintic function. And I'm just going to sketch in the general shape of what these functions look like. So let's start with a constant function. A constant function is a horizontal line. So I'm going to draw in a horizontal line. Okay. It doesn't matter if the horizontal line is up here or down here. We're just trying to get the general shape down. So the general shape is a horizontal line. The degree for a constant function is 0. So degree is 0. All right, we're going to go down to number 2, a linear function. I'm sure you remember what a linear function looks like. It can have a positive slope or it can have a negative slope. So a linear function is going to look like this. And the degree for a linear function, and I'm going to abbreviate, the degree is 1. So this is a positive slope. If it was facing the other direction, it'd be a negative slope. Number 3, quadratic function. A quadratic function is a U shape. It could be a parabola that's opening up or a parabola that's going down. I'm going to make mine open up. So there we have it. And my degree for a quadratic function is 2. Number 4, cubic function. The number cubic means 3. So a cubic function can go up, or it can go down, up, down. So I'm going to draw mine as going up and then down and then back up again. So a cubic function can go up, down, up, or if I started the other direction, it can go down, up, down. So this is a cubic function, and my degree is 3 because cubic, the degree means 3. Quartic, it can go up, down, or down, up. So I'm going to draw one that looks like this. Again, this is not the shape of what every single quartic function looks like. It's just a generalization. This is not the shape of every single cubic function. It's just a generalization. So for quartic, the degree is 4. And it can go down, up, or up, down, down. So quartic means 4. And quintic, I'm sure you probably caught on to it. Quintic is 5. So 1, 2, 3, 4, 5. So quintic means 5. There's 1, 2, 3, 4, 5. So this quintic function went up, then down, then up, then down, then back up again. So degree 5. So these are the general shapes for a constant, linear, quadratic, cubic, quartic, quintic function, and we've labeled the degree. Again, just generalizations, not what every single one will look like, just a generalization. Now I'm going to go through and I'm going to introduce something called a turning point. The turning point is exactly what the name says. It's someplace in your graph where it switches directions. So where it changes from positive to negative, or where it changes from negative to positive. That point is called a turning point. So for these first two functions, if I look at a constant function, it's going the same direction the whole way across. It's going this one speed, one direction, all the way across horizontal line. So there are no turning points. So turning points. There are no turning points for this first one. If I look at this linear function, it's going to be going in the positive direction forever and always. So there are no turning points in that direction either. So I'm going to abbreviate TP. And there are no turning points for that one as well. Now, as I get into the other ones, there are going to be some turning points. There's going to be some point in my graph where it switches from negative to positive or positive to negative. If I take a look at this quadratic function, it's going down and then all of a sudden it stops, and then it starts to go back up again. So my turning point is somewhere down here. So there is one turning point. If I take a look at number 4, I'm going up, then I go down. So there's a switch, there's a change in direction there. That's called a turning point. Then I'm going down and I go back up again, and there's a switch there. So this particular function has 2 turning points. So we'll label that 2 turning points. Number 5 is a quartic function. I see it changes directions here, it changes here, and it changes here. So it's going down, up, down, up. So there are 3 different turning points here. So 3 turning points. And for number 6, a quintic function, you guessed it, it changes here, 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 and here. So there are 4 turning points. Turning points are also your relative max and mins. So if I'm looking at a quadratic function, this is actually the minimum. So this one turning point down here where the red dot is the one turning point for a quadratic function. Is the minimum. These other ones, I can have relative maximums and relative minimums. So it's where your graph is changing from positive to negative or negative to positive. Now, I want to take a look at these numbers, and maybe we see like a pattern or a generalization that we can make. With the exception of possibly maybe the first 2, maybe you see a relationship between the degree and the turning point. So my degree, which is the highest exponent, is 2, and I have 1 turning point. My degree for number 4 is 3, and I have 2 turning points. My degree for number 5 is 4, and I have 3 turning points. This one, degree 5, and I have 4 turning points. So the relationship between the degree and the turning points is that your turning points is going to be 1 less than your degree. So just a general summarization of what we're doing up here. Your turning points will always be 1 less than your degree. It'll be less than whatever your degree is. So if my degree for a cubic function is 3, I'll never have 4 turning points. If my degree is 4, I'll never have 7 turning points. My turning points, which are my maximums and mins, will be less than my degree. So that's a generalization that you should have from up there. Now, let's take a look at how to recognize if it's an even or odd degree function. So let me read through this statement. Odd degree functions will always have an odd number of real zeros. So that's important to recognize what a real zero is. Even degree functions will always have an even number of real zeros or no real zeros at all. So let's go through these words before we take a look at these graphs and try to figure out which is which. So it says if I have an odd degree function, so degree 3, degree 5, degree 7. If I have an odd degree function, there'll be an odd number of real zeros. Real zeros is where your graph crosses the x-axis. So you graph it, use Desmos, ta-da, look and see where it crosses the x-axis. Those are your real zeros. Even degree functions, which would be like degree 2, degree 4, degree 6. If I have an even degree function, they'll have an even number of real zeros or no real zeros at all. So I have 4 graphs down here that we're going to go through and label how many real zeros that there are. So 4 different ones down here that we're going to label. Okay. So let's take a look at the even ones over here on this side. So I got this even degree polynomial. We're going to state how many real zeros there are. A real zero is where it crosses the x-axis. So here's my x-axis here. This function is not crossing the x-axis, so there are 0 real zeros. It doesn't cross at all. And to be specific, we can label what kind of degree this is. 1, 2, 3, 4. So this is a degree 4 polynomial. So it's a quartic polynomial, and it does not cross the x-axis at all. So there are 0 real zeros. Let's take a look at number 2. I see that it crosses the x-axis 1, 2, 3, 4. So it crosses in 4 spots. So there are 4 real zeros. And this is also a degree 4 polynomial. 1, 2, 3, 4. So this is also a degree 4 polynomial. So these are even degree functions, and as the rule says up here, even degree functions will have an even number of real zeros, like number 4, that's an even number, or no real zeros at all. Let's take a look at our odd degree polynomials. So odd degree, this one is 1, 2, 3. So this one is degree 3. And number 4 is also a degree 3. 1, 2, 3. It's a degree 3. So we're going to label how many real zeros there are. This one is 1, 2, 3. So real zeros is where it crosses the x-axis. There's 1, 2, 3. So there are 3 real zeros. This one here, how many times is across the x-axis? 1. So there's 1 real zero. So odd degree functions will have an odd number of real zeros. This is an odd degree function. They have an odd number of real zeros. So this is just illustrating what our rule says up there at the top. Odd degree functions will always have an odd number of real zeros. This is my odd degree section over here on the right. Even degree functions will have an even number of real zeros or no real zeros at all. So that's over here on the left side. So how can you tell by looking at a graph the number of real zeros? It's where it crosses the x-axis. So where it crosses the x-axis. So this is a very important question. How can you tell by looking at a graph the number of real zeros? It's where it crosses the x-axis. Your degree, which is your highest exponent for the polynomial, tells you the number of zeros, which are real and imaginary. So the degree of the polynomial tells you the number of zeros, real and imaginary. So if your degree is 5, and there's 3 real zeros, then we know the total space that we're looking for is 5. So 3, if I take away 3 from 5, that's going to give me 2. But that's coming up in another video if you didn't get it right there. But these 2 notes down here at the bottom are very important.